actually, this work, more or less, it started with differentiality after the last Hadamard conference in Budapest. And I have to admit, I had scheduled it for 2 years ago. Then it has been idling almost all the time. So a lot of the results are in some sense very old, but we are starting now kind of refreshing the topic and getting up. So some of the open questions are things we are just about to resume now. So my idea is kind of since we also have a slightly mixed audience, to start just with the Circulant Hadamard matrices, we will see that it connects to a problem that is more kind of in computational algebra, the so-called cyclic n-roots problem. It connects to another problem, mutually unbiased basis, also something we will hear later this week, or maybe even today, this afternoon about. We are using a little bit of numerics. There I have to say I'm absolutely not a numerics person, I'm more an algebra person, so that's imported kind of results by other people. We are using symmetries, that's again more to my heart, to really exploit symmetries, which leads us to the main idea of this talk, to use invariants to break down the problem, and then we get to some results and open problems. So the question, what is a circulant Hadamard matrix or complex Hadamard matrix? We're just writing down a circular matrix, that is, we're fixing a first row, then we're shifting it by 1 up to n. So we get the circulant matrix and then the Hadamard condition. We are using kind of the standard, or say one of the two standard normalizations. Here we are saying that each of the entries has modulus 1. That gives us the condition that the matrix times its adjoint matrix, or the complex transpose matrix, is n times the identity. And the condition that we have the modulus of each kind of unknown variable being 1, that means that the complex conjugate is actually the reciprocal of it. And that's the approach we are taking. We are trying to write down some equations on that and saying, okay, in order to formulate what is the adjoint matrix, I'm using this condition 1 over xi, which clearly is a general condition, not just constrained on the unit circle, but we will come to that later. So when we write it down, just for not 10, that would have been too busy a slide. I just took the example half the size, matrix of 5 by 5. So the adjoint matrix, the complex conjugate transpose, now becomes the 1 over xi matrix. And then when we write down the conditions that the two matrices multiplied with n times identity, we will see if we multiply the first row here with the first column there, we already get 5. So 5 times identity is on the diagonal. And the only conditions we have is for kind of the off-diagonal terms, that the vectors are mutually orthogonal, and that gives us these conditions that we have some ratios of variables summed up to being 0. In all of that, we will have more physics language, a phase degree of freedom, so we can multiply each of this initial vector by any number on the unit circle, and we can remove that by fixing, for example, setting x0 to 1. So in the literature, you will find circulant complex Hadamard matrices with diagonal 1. That's what this amounts to. And that's just removing some of these degrees of freedom we have. Although I have to stress is that the usual kind of notion of equivalence, we would allow the columns and the rows be multiplied by something of modulus 1. That clearly does not preserve in general the circulant property. So we are losing that type of property. We still might have some equivalences induced by that, but in first place, the only degree of freedom is multiplying one of these rows, as that since multiplying the columns here by some phase factor would destroy, in general, the circulant property. So we just take these equations. I wrote them down now as kind of proper fractions. And the question is, how can we change this set of equations into something more nicely looking, just polynomial equations. And in order to clear these denominators, that would be one of the things that we just say, okay, we bring everything on the common denominator. Then we get high degree, kind of a degree 4 in that case, since we have to multiply always by all the other variables which are missing here. We can introduce new variables, which are just the ratios here. And I walk you through that. So we are just replacing x0 divided by x1 by a new variable y0. And we go on just with all the other ones. We're just replacing all of them with our new variables. So what was kind of a degree 4 numerator polynomial now just gets a linear relation for our variables. In first place, we cannot do the same with the second one unless we would introduce new variables, but we still want to have them coupled. So what we are doing instead is we multiply just by the corresponding kind of terms, x1 over x1, so just by 1, x2 over x2. And now if we swap the two terms in the denominator, we will find, okay, we have now x0 divided by x1, x1 divided by x2, and that's nothing but the product of the two variables. So we make the substitution and we get the product of the two variables, and then just in the same fashion, we can continue. And what we get now is we get, for this second orthogonality conditions, we get the simple equation y0 times 1 y1, y2 times y2, 1 times 2, and so just circulant shift of our product of two variables. And when you go on, you will find the very same. The third equation will be the product of the first three, and then the circulant shifts, the sum being 0, and the fourth one gives us the product of four variables, and then circulant shifts. So it's a very kind of innocent looking set of equations. And actually, we are adding even one more equation to that set. What we are doing is we are adding a trivial equation, which, if you look at that properly, every variable occurs in the numerator and in the denominator. So this is just equal to 1. But in terms of our new variables, this changes that the product of all variables equals to 1. And that at the same time eliminates potential additional solutions we get by the substitution where some of the variables vanishes. Since clearly we don't want any of our denominators vanishing in our expressions. So that system of equations, that is what is known in the literature as the cyclic en route problem. It's, again, kind of very innocent and simple to describe system of equation. First, we take the sum of all variables being equal to 0. We take the product of first two, making all the cyclic shifts being equal to 0. We're taking three variables. We're taking n minus 1 of the variables. The product and that kind of, again, with all the circulant shifts. And then the final equation is taking the product of all of them. Clearly, there we don't get our n terms, we just have one term, and that's equal to 1. It turns out that, and that's also why the name comes in, that you can take kind of the standard rational roots of unity, and for odd n, you just take consecutive powers of them, and they will obey the system of equation. For even n, you get a slightly more complicated formula, and even kind of, you might have repetitions, but basically there are some which also refer to as classical solutions, already known at least since Gauss, to these equations, but we will see, or I don't write them down, but we will also have solutions which are actually not roots of unity. In the rational sense, of course, all of them have to have modulus 1, so that's a condition to check. And then when we want to go back to our Circulant Hadamard matrices, we have to make the resubstitution. And then it turns out we had the normalization that the first component actually should read x0, but clearly It's invariant under cyclic shifts, our solution space. So the first component is 1, then 1 over y0, then 1 over the product y0 over 1, and up to n minus 1 of the variables, the product. So the question now is, how many solutions do we get as a system of algebraic equations? And what is maybe not that much known in this community, there is Ernst Jagiellonian, who is more from coding theory and sequences. He looked at this very early. He made the statement, and there are only finitely many solutions. When I looked at his papers, he also says a kind of, I know how to compute, but he didn't give the formula. But then in a later paper by Hagerup, he said for prime dimensions, we have this kind of central binomial coefficient, which gives us the number of solutions for this system of equations. And that will actually include solutions which are not on the unit circle. Clearly, we have excluded the zeros, but still we have additional solutions which are not solutions to our original problem. Then also something that has been known very long, I nonetheless put a kind of more recent reference by Faucher, since he has a nice explicit kind of formula and construction for that. Whenever our dimension contains a square factor m, or m squared, then we have at least m minus 1 free parameters in the system. I don't know whether this is still a conjecture, kind of one knows that at least that many. It might be that there are some cases where you get even more solutions. And then something which is still kind of quite often stated as a conjecture, but again, Jagiellonian in his work, and there's also a technical report, which will be at the very end of my references, and I'm happy to share the slides with everyone. So he has also proved that when the dimension itself is square free, we have finitely many solutions. But since we have the central binomial coefficient, the number of solutions is growing exponentially. And I just give you this number. So for the small cases, you still have moderate numbers. 4, 8, and 9 are non-square free numbers. And related to that, kind of we have infinitely many solutions. We have 3 parameters. But for the case we are in particular interested in the talk, for dimension 10, we have almost 35,000 solutions. And then the next case goes up almost a factor of 5. Or actually, it's more than a factor of 5 in the number of solutions. Then 12, again, not being square free, we have infinitely many. And then we have 2.7 million for dimension 13. Those numbers, in particular for 11 and 13, are actually to some sense coming from the numerics community. And clearly, since those are prime numbers, they are matching this one. But also the number 10, we will see it. In first place, it came from the numerics community. Say the problem is that this work I'm referring to here, that was from the IEEE conferences, which back then had printed proceedings, and that restricted to one-page abstracts only. So there it's clearly only stated, but there is a technical report which was hard to get hold on. I got it directly from him 10 years ago, and there is an explicit proof. There is an explicit proof. I admit it's plausibility proof or check that I did. I did not look at all the details, but it looked reasonable to me in that sense. You might have some doubts when you look at it. So the question now is, what is the situation when you really want kind of to avoid all the numerics? And it turned out kind of maybe up to dimension 6, and that was a little bit how I got into this question, this connection to mutually unbiased basis, and was thanks to Ingemar, who pointed out related works also for dimension 7 by some his Swedish math colleagues, Björk and Fröberg, in 94. So they did dimension 7. They actually also did dimension 8, still in the 90s. Dimension 9 was done by Fougère. And dimension 10, you will see a bit more in my talk, that was essentially done something like 3-4 years ago by us, but clearly not published, and there are also some of the details still a little bit missing. So what is the situation? What I'm listing here? We have the total number of solutions. That's essentially what we had before. What is different? So in dimension 4, it turns out we really have only one parameter and nothing else but these one parameter solutions. In dimension 8 and dimension 9, it actually turns out we have kind of an infinite part of solutions, but then there are some sporadic isolated solutions. It's 1152 in the case of dimension 8. It's 6156 in the situation for dimension 9. And dimension 9 is special in the sense that we already have solutions with multiplicity. That's also why in the result by Hagerup, he's counting if including multiplicities. We are not aware of examples in prime dimension where we have multiplicities for the solution, but it shows up in dimension 9. What I give here is just the mere number of solutions. The question is, when we look at those solutions, how many of them are unimodular, so that they have modulus 1, that they really give rise to complex Hadamard matrices, and typically that's much less. Not in the small cases, but the bigger we get, kind of the fraction of solutions on the unit circle, and they're really all the coordinates have to lie on the unit circle. Sometimes 2 or 3 of them lie on the unit circle, the others not. That is getting smaller. And what the final one here says, that's now more going into algebraic geometry. We have algebraic equations, we have corresponding varieties to it. And then when we make a primary decomposition of our ideals, we get a decomposition of the variety into irreducible components. And just to explain also the notation, in dimension 4, we actually get, in first place, from our system of equations, that has 8 components. But the components are not primary. So in terms of the varieties, we have non-radical ideals which share the same variety. And if we go to the radical, the primary decomposition, it turns out that there are 6 out of the 8 components. They are actually 0-dimensional, so they are kind of isolated, or say they are just points, but the points are not isolated. They are part of the one-dimensional components. But that's just that our system of equation, in some sense, is more complicated than just describing the various solutions. And also in higher dimensions, we have the solutions kind of with multiplicities. So this decomposition was computed by Björk and Fröberg for dimension 8. Fougère did it for dimension 9. So there are 3 two-dimensional components and 110 components which are 0-dimensional, corresponding to these isolated points. In dimension 10, I'm writing we have at least 317 components. That's related to the fact that for some of the components, we have not yet computed the full decomposition of them into irreducible components. So some of them might split further, and that's why we have at least 317 components. So what is the connection to mutually unbiased bases? And for that, I first have to state what are mutually unbiased bases. It's just orthonormal bases written in physicist notation in this cat. So the I labels the index of the basis, the J labels the index of the variable within the of the vector within the basis, And what we want is if we take the inner product of vectors coming from two different bases, then the squared overlap between them should be 1 over d plus 1. So yes, I'm mixing n and d here. So it should be n in this case. So examples that we have is we can take the standard base and the rows of the Fourier matrix, of course, alternatively the columns of them. And related to that, kind of, we can actually take the standard bases and any rows or columns of a complex Hadamard matrix, which we normalize to have modulus 1, since we want orthonormal bases. So that's the other type of normalization we could have for complex Hadamard matrices as unitary matrices. So they always form a pair of mutually unbiased bases. One of the big questions, I think some might have, or clearly some of you have worked on that question, is when for any dimension the maximum number is n plus 1, and we know that if the dimension is a prime power, then we can reach this maximum. There is kind of a almost trivial lower bound for those who are more in kind of combinatorics. It's like the McNish bound in terms of Latin squares or kind of orthogonal nets. When we have the prime factorization, then it's the smallest prime power plus 1, which gives us a lower bound on that. There is one construction known to me by Wojcian and Beth, which are using mutually orthogonal squares, which is able to beat this lower bound, but it has to be a dimension that contains a square factor. And the smallest example I commit to memory is 26 squared. There might be other examples, but whenever you have 2 times an odd number, the lower bound is 3. And to me, one of the most annoying questions is, can we find in any dimension of this form at least 4 bases? So that was all a little bit kind of behind this idea. Let's start with the Circulant Hadamard matrices and see whether we get out of those more than 3 bases. There is this other connection kind of to the world of sequences, and that's what they call biunimolar sequences. So that's a sequence here is actually just a finite sequence, a finite vector. And biunimolar means that the vector itself and the Fourier transformed vector both have modulus 1 in the components. And it turns out that this is exactly the condition to have perfect autocorrelation. That means, of course, the sequence, the correlation of itself has to be non-zero. But if you have any shift of the sequence, then you get a correlation of 0. And that's, in terms of synchronization of signals, what you want. And it turns out that the sequence is biunimolar exactly if after this transformation, we get a solution to this cyclic n-root problem with modulus 1. So we see kind of many different ways of formulating the same problem, since although this perfect autocorrelation is nothing but having a Circulant Hadamard matrix. So it turns out from this setting, then if we take the Fourier matrix and the standard basis as our pair of mutually unbiased bases, then whenever we have a Circulant Hadamard matrix that corresponds to a solution of this cyclic n-root problem, corresponds to sequences with perfect autocorrelation, we actually have a triple of mutually unbiased bases. Unfortunately, in all examples, for all the dimensions I've checked, we get stuck at 3 with this approach. Unless it's a prime dimension, of course, then we get the full solutions. So let me briefly kind of switch to the numerical approach to this problem. And now I'm going back to this kind of simple or innocent looking system of equation for the n-root problem. We have n equations in n variables. although thanks to this additional kind of trivial equation that the product equals 1. So what we can do is we can have a high-dimensional Newton method. We just pick a random initial point and we apply this Newton iteration, and it will converge to some solution. Of course, we don't know whether we have all solutions, but we just can get one. There is something more recently, which is actually quite simple idea, that is based on the approach of bidimensional sequences. So that's now in the question of circulant Hadamard matrices. You just start with a random vector, where each of the components on the unit circle. You compute its Fourier transform. You rescale every component to lie again on the unit circle. You apply again the Fourier transform. You just alternate these steps. And what Für, and I'm not able to properly pronounce it, his Polish colleague, they should snick or whatever, kind of what they, I think he's from Wrocław, but I'm not completely sure. So for me, also my communication was with Für, who is in Germany, also, but you could guess from the name. So they proved it more generally. You can replace the Fourier matrix by other unitary matrices. And they were investigating conversion of this process and what you get from that. The method, which I just stated and really cannot comment, maybe some of you can help me with that during the week. There is so-called homotopy continuation method, which is a kind of simple, if you look from the physics perspective, you have a system of equation, capital F of C, so C is multiple variables, and you have your target system of equation, G of C. And what you do is you vary the parameter T from 0 to 1, transforming kind of the system of equation from F to G. And then along this path of transformations, kind of you hope that you preserve with kind of this small perturbation your roots. And then there are methods for kind of counting how many roots you expect for your system of equation and how to transform this. And that is where several groups, I have the reference to a Japanese group, but there's also Jan Verschelde in US who did a lot of work of that. And they use the cyclic n-root problem as one of the kind of benchmarks to test their methods. And there is actually also at one source, I have a solution for dimension 14. I'm not sure how they really, what I read just more or less from the abstract of those papers, that you can certify that you have the correct number of solutions found and that you get them to a certain approximation. And that is actually something that we have also used. So we just took from their web pages. Some of them are no longer available, unfortunately. We took this set of solutions and used partial information you will see in 2 slides in which way to get the exact solutions. Also in the world kind of computational algebra, the cyclic n-root problem became kind of a benchmark. So it was really an achievement for Scher when he, with his new method for Gröbner basis calculations, was able to do dimension 9, now 20 years ago. He wrote that he had done dimension 10, but at least all what I found was he did some modular computations for one fixed prime, which gives you some information, unless you were unlucky with the choice of your prime. But at least to my knowledge, nobody has really carried out these big calculations. Just to give you a bit of an idea, I'm saying it's huge coefficients, large degree. That is what the dimension 5 problem, which was kind of this innocent set of equations, when you calculate a Gröbner basis with respect to lexicographical order, that allows you to solve explicitly for the solution. So I have here one equation of degree 15, only involving y4. Then we have equations involving y3 and y4. So if you have solved for y4, you can plug that in and you solve the next set of equations. you might also run into kind of conflicting equations. That's why you still have two of them. Then you have a set of equations involving kind of 3 variables, 4 variables, and then the final one is kind of this trivial one, which is just that the sum of all variables equals to 0. It's also kind of the question you could ask. I said we have 20 components. It's not immediately to see how the 20 components arise here. The only thing you kind of can imagine or spot is this polynomial is actually not irreducible over the rationals. So that already kind of splits into subcases. And then if you carry that on, you get a set of equations over the rationals, which corresponds to these 20 components you have. So what we are using to solve the problem is actually symmetries, and they are nicely described in the paper by Björk. What are the symmetries? And this X here should be removed. That's a typo. So we have cyclic permutations. Since our variables only involve, our equations only involve rational coefficients, so complex conjugation is an invariant, but also taking the reciprocal. Remind you, the two agree on the unit circle, but not in general. So in general, those are two different symmetries. You can also reverse the order of the variables. You can multiply all of them by an nth root of unity. The constraint to the nth root of unity comes from the fact that the product of all variables has to be 1. So what you multiply with has to be an nth root of unity. And then there is a more complicated operation, which is called association. You replace a variable by a product of other variables. And that's more easily seen if you go back to the original variables for the Circulant Hadamard matrices. Then a permutation, when you have something that is co-prime to the dimension n, if you multiply each coordinate by this element theta, you have a permutation which normalizes the cyclic group, and that's why you have this additional symmetry. And if you apply this permutation to the original variables and then transform it to the other variables, you get this kind of type of transformation, which again kind of is a symmetry of the problem. And how are we using this symmetry? We are trying to use the symmetry to decompose our problem into kind of irreducible components, or say into smaller components. And for that, what we do is we consider an invariant, actually only one, you could use more of them, with respect to the symmetric operations. And it turns out for dimension 10, we get this particular rational function. The construction here makes it kind of circulant invariant. Here you see kind of always reciprocal pairs. Going from this one to that one is this association. And so overall, kind of you can verify that this is actually an invariant. It turns out that you can replace this by a polynomial invariant, since the common denominator here is just the product of all variables, which if you add the other equations is equal to 1. So what we can do is actually, at least in principle, we can add a new variable to our system of equations and say z minus this variable minus our invariant with the clear denominator should be 0. And that gives us an equation telling it what are the conditions for C for this to be 0. That tells us what are the possible values of our invariant. I have actually, that's a very recent result from last week. I have carried out this calculation, which can be done without solving the full system of equation. And it turns out we can calculate this polynomial here in something like 5 days. It's not solving the full problem, but it gives us a polynomial, which originally we actually were computing just these values, taking all the numerical solutions. We find 63 different values, of course, within some epsilon environment. we multiply kind of all these linear factors together, we get a polynomial, which is a polynomial supposedly over the rationals. And if we have our solutions to sufficient precision, then we can just take kind of these floating point numbers as our rational approximations. And it turns out that this polynomial is the very same I have just kind of verified by direct computer algebra methods to be equal. And now this polynomial of degree 63, it actually splits into 18 factors. So we have 5 linear, 5 degree 2 factors, 2 of degree 3, and so forth, and kind of 2 big ones of degree 12 and 14. So we can split our problem into 18 subproblems by just adding this equation, which was just a condition that the variable c equals our invariant with clear dominator. And we are using this minimal polynomial or a factor, that polynomial of our invariant to say the variable c is constrained, say if it's linear to this particular value. And then when we carry out these calculations, we are able to calculate the Gröbner basis for them. Some of these calculations really use the tens, if not the hundreds of gigabytes of memory. There are also modular techniques involved. Whoever's interested, I can talk during the week. And then we compute the decomposition into irreducible variety. So that's in some sense, again, a standard procedure in computational algebra, but you have to play tricks when you push the borders. And for the 2 biggest cases, actually, we have not yet done that, splitting completely. So if we take the first 16 of them, we get 311 components. And what I'm writing here is a little bit abusive notation. It means we have 20 components which only have 2 points. We have 15 components with 4 points and so forth. But then there are kind of big components which have 960 or 3,200 points in them. For this factor of degree 12, we were able to split it at least into 5 additional components. Each of them have 1920 points. And it turns out that among those, we actually have unimodal solutions. And what is also not yet fully confirmed, we get numbers of modulus 1, which have a minimal polynomial of degree 960. And since we have quadratic equations involved, which I don't know yet whether they split in the same field or not, we might have another degree 2 extension. So we have a considerably high degree kind of a description of some circulant Hadamard matrices in order 10. The last factor actually has 11,200 solutions, but at least from the numerics, we know there are no unimodular ones, so they don't give rise to complex Hadamard matrices. So in some sense, we can ignore them, but at the end of the day, of course, we want to complete that step as well. So that's something still in progress. Also now with improved computing power. And what I stated before, which is also confirmed for all these components, that there's a little bit of this numerical uncertainty for the big ones still. We only get about 1/10 of the solutions being unimodular. So clearly, if we have 3040 solutions which are invariant under cyclic shifts, we only get 1/10 out of them circulant Hadamard matrices, and almost all of them are of non-Batson type. That is, in most of the cases, we don't have roots of unity as our solutions. We have some kind of algebraic numbers which under certain embeddings gives us complex numbers on the unit circle. What we can do here is we can just take our 3000 vectors and test which of them are orthogonal to each other. And it turns out by just recombining them in total, we get 1136 complex Hadamard matrices from these solutions to the Circulant Hadamard matrix problem, but only about kind of 1/3 or 1/4 of them is really a Circulant Hadamard matrices. The others are recombinations of them. And actually all of them, also these other ones, they give rise to triplet of mutually unbiased bases. But it turns out that if we would go for a fourth basis, it clearly has to come from the set of bases we have already here from our vectors. And so we can just simply test, and we find that actually there is not even a single vector that is unbiased to 3 bases we are choosing. So we are getting stuck with 3 bases. So what we achieved is complete classification. I put there still an ongoing complete classification, let's say it, of the solution, since we have not yet done the last step for the final, the big components. What we are still kind of a little bit as an outlook, we just really have resumed that to classify which of them, of the 300 for the Circulants we get, are really inequivalent or not. It's kind of a straightforward calculations, at least to find inequivalent ones. For the remaining ones, there might still have to be some additional work. And then clearly, also the question is, when we have these 1100 matrices, in how many different equivalence classes do they split? Clearly, kind of a bit of more, not directly to this approach related outlook is, can we find more 3 mutually unbiased bases in dimension 10? Kind of the bottom line is when we start with the standard and the Fourier bases, we are not getting 4, but they are clearly more than just the Fourier matrix as the first kind of non-trivial choice for our second basis. So in principle, we can carry out similar programs, writing down the equations, something Stefan has done some time ago for smaller dimensions in quite some detail. But the problem is already kind of for the Circulant problem, we have exploding kind of systems of equations, and at least my attempts with other Hadamard matrices, they're indicating similar problems. And then another step which we have partially started is for dimension 11, taking the numerical data, we actually find a polynomial of degree 69. So it's not that much bigger, but the problem is that doing the Gröbner basis for the cyclic n-root problem, even when we constrain it to some sub-problem using factors of this invariant, is something which is at least not easy, and where we are still hoping kind of to have new ideas. So with that, I want to thank all of you, and I want to thank all the responders. And just also for the record, I want to show some of the references, and maybe I will fix at least this one typo I spotted now, and then maybe they will be available through the web page of the conference. So there's a second set of, but let me go back maybe just to this outlook, and thank you for your attention.